Up till now, we've talked more in general terms about how we get a state from a trapped ion. Now let's get down to specifics. And when I say specifics, I'm going to go straight to a particular ion. And that's going to be the, watch how you pronounce this, it's Ytterbium. Ytterbium, not titanium, but Ytterbium. And that comes from a Swedish town where they had a lot of rare earths that were found in a quarry. So that's background information you may not want to know, but it was interesting to me. Anyway, notice that on this right-hand side here of the periodic table, there are 6 levels here. Count them: 1, 2, 3, 4, 5, 6. This happens to be the S6 level that is filled with 2 electrons. What we're going to deal with is the ion. So what we do is we take this metal, we bang it with something to knock off one of the electrons. And once we knock off one of the electrons, then it takes on a charge of plus. The ytterbium has 70 protons, and it has, if we talk about ytterbium isotope 171, which is the one we're interested in, the 171 happens to have, 70 protons, 101 neutrons. So there's a whole bunch more neutrons than there are protons. If it's balanced, there are 70 electrons, but in our ion that's created so that it has a charge so that we can move it around, it only has 69 electrons. Now, one thing I should mention before we go further, the isotope 171 is chosen because the nuclear momentum number is 1/2. And because that's 1/2, that's going to work well with that single electron, so that single electron will have a spin of 1/2. And if I remember this correctly, it'll match up with some of the information that's coming up. Okay, we've identified our ion, and now what I'm going to do is start at the nucleus. What's in the nucleus? Protons and neutrons. And each proton has a property of spin, and each neutron has a property of spin, and these nucleons are all rotating around in the nucleus. So as they rotate, they have angular momentum, and as they have spin, they have this property of spin. Now, because it's an odd number of neutrons, the spin is 1/2 overall. So you don't think about the nucleus as having a spin property, but it does have a spin value of 1/2. Now, why 1/2? I'm not going to go there. That's one of the quantum numbers, and let's just live with it that when experiments are done and so on, it has to be 1/2. So the nuclear spin is 1/2. Now, what about the electron? We designed this so that all these electrons fill the shells as they move out. Remember, there's 69 of these crazy electrons, and when we get to the S6 level, there's no angular momentum because that particular orbital is the simplest one, and it doesn't have any angular momentum. In other words, the rotational momentum. So, what about when the spin property of the nucleus interacts with the spin property of the electron? Well, either the spins are going to add together or they're going to subtract. So when they subtract, the spin level is, or the overall level between the nucleus and the electron is 0. And I won't go into why the letter F is used, mainly because I don't know, but there's a letter F that's used for the overall atomic momentum factor, which includes spin and angular momentum. So let me bring up the page here, and we see nuclear spin equal to 1/2. It leads to only 2 hyperfine levels. Now, what's interesting is these hyperfine levels are not electron energy shells, so to speak. So we're not actually advancing the electron a whole energy level, like I was probably discussing in an earlier video, but it's a hyperfine one. And what's nice is when it bumps around between these two, between the F equals 0, where it's I plus J is 1/2 minus 1/2 equals 0, it is 1/2 plus 1/2, which equals 1. So these are the 2 levels, and it makes a perfect 2-level system. Now, to show you how close these energies are, they're only 12.6, and this number can be drug out to many more digits, to a gigahertz splitting. So the energy levels are compared to the overall energy, which is in the optical range, which is in terahertz or trillions of hertz. We're only dealing with billions of hertz. So how do we come up with a 12.6 gigahertz signal? Well, that's microwave levels. So you could use a microwave, but usually what's done is 2 lasers are used with a difference frequency equal to this magic 12.6 gigahertz. And that's how we change the states. To recap, have this picture in your head. We've got this positively charged ion, which is this strange element called Ytterbium. The Ytterbium happens to, with this positive charge, also has properties that make it to where the spin level, overall spin level or overall angular momentum, can be 0 or it can be 1. So these 2 levels can be measured with another laser, a measuring laser. Now, I'll go back and listen to this and see if it all fits together, but I think we're ready to move on from here.